Okay, you don't need to know this proof for this class because we just use this rule that this integral in this form is going to be the inverse tan function. Now, I guess you wouldn't see it as the inverse tan integral proof because this isn't actually the inverse tan. This would be more the derivative of the inverse tan rule, kind of working backwards. But I just wanted to show you this why. This is to do with partial fractions because I think that this is important to see why in this case and kind of see how some of your calculus professors will do these proofs and how they'll come about it. So I'm going to go about this. You don't have to know this. I would write it down and have it so that whenever you kind of go to it, you can kind of try to follow it. And even more importantly for next year, if you've got to use it, you can say, when you have the question, well, why is that? You can look back and see how it comes about. So we're going to end up doing kind of a double substitution thing here. So hopefully it makes sense on the second substitution because we're going to bring in trig stuff. So the first things first is we're going to, this is the way I would do it, is I'm going to divide this bottom stuff here by the a squared. Okay, so I'm going to divide everything here by an a squared. Okay, so now my next line is going to look like this. Now this is just going to help us solve it later. Now, if this wasn't an a here, if this was just 1, it would be really easy, but it's not. But dividing that a squared by a squared makes it a 1. And you'll see why that's important soon. So we get dx over a squared. Now, that a squared that I just put there, that's actually a constant. I could take that out right now the way it is, but we don't need to. You'll see right away. So here's where our first substitution comes in. I'm going to write it in blue. I'm going to let u equal x over a. Okay, so now when I take the derivative of that, that's going to be 1 over a dx. So like I said, that this a squared here is a constant, but it'll kind of clear itself up. So I'm going to substitute that on this page, and then I'm going to flip the page, and we'll kind of do the second substitution there. So I've still got an a right here. You can see I've only got one a here, so I'm going to take the 1 over a that's left out, and I'm going to have 1 over u squared plus 1 du. Okay, so I took the 1 over a out front in place of that dx. There's still a 1 over a that gets taken out. So like if you look here, if I took this a squared, I could write it out as 1 over a. Oops, this isn't going to work here. I could write it out like this instead, over a, and put 1 over a out front here. That's still an a squared there. All right, so let's kind of go over that again here. I'll erase that one more time. So remember, we had dx over a squared here. But I'm saying we can split that a squared up into 1 over a times the 1 over a there. So now you can see where this part gets replaced with the du. That's where that du comes in. And we're still left with that 1 over a. Okay, so now we'll cut that over to the next page. So we're going to have 1 over a integral 1 over u squared plus 1 du. So that's where we're at. Now we have to, this is where the second kind of substitution comes in. I'm gonna put this one in green here, and we're gonna say let u equal tan theta. That's right, tan theta. Okay, so now the derivative of u equals secant squared theta. Now, if we go and do that, we get 1 over a whoops, I should do that back in blue again. 1 over a integral 1 over tan squared theta plus 1 secant squared theta d theta. Well, no matter what we do here, it's going to be kind of a crazy thing to try and simplify, and the whole works as well. So here's where we get a little creative. Remember, from identities, sine squared theta plus cos squared theta, equaled 1. And from there, we had a whole bunch of identities that we can make up, like sine squared theta equals 1 minus cos squared, and cos squared theta equals 1 minus sine squared, and things like that. But one thing that we don't spend a lot of time is doing identities for tan and stuff like that. So I'm just going to divide cos squared theta out of everything to make a tan squared identity, or a secant squared identity for that matter, right? So you can see sine squared over cos squared, well, that gives me tan squared theta plus cos squared over cos squared is 1 equals 1 over cos squared, well, that's just secant squared theta. So this is just using that simple idea of identities, and we can see we've got tan squared theta plus 1 is equal to secant squared. So I'm going to go back over here and substitute that in place of the tan squared theta. So I'm going to have 1 over secant squared theta times secant squared theta d theta. And it wouldn't matter if we substitute the other way too. It wouldn't change it. Well, now that means I can cancel this and this out, and I get 1 over a integral of 1, or I could just leave it as d theta, it doesn't matter, d theta. And now I can go and do the integral of this. So the integral of this thing here is 1 over a. Integral 1 is theta, right? Well, and what is theta? Well, let's go back over here for a second. Let's circle this guy up. To get theta, we'd have to inverse tan. So tan inverse u is equal to theta, right? That's using what we set up here, u equals tan theta. I could have done it there. I should have done it there. It was inverse tan that to get theta, but we didn't know that we were going to get theta. So now when I come back to this last step, I can now write it like this. And I'm just going to slowly substitute back in the other stuff we know. So this 1 over a times theta is now 1 over a inverse tan of u, which we know we used the substitution of u equals x over a on the other page. So now when I go one more step, I get 1 over a inverse tan of x over a plus a constant. So there's the big ugly proof, and I know it seems like craziness, but that's just using the different trig derivatives that you will know when it gets there. And the only reason I even do this one is because we see this, like I said over here. Oh, I never even said, oh, I did say it. I wrote it right here. Very common in partial fractions. So, again, anything in the form of 1 over x squared plus a squared, or it could be a constant on top. It could be like 3 because you can just factor that out. But as long as you can get it in the form of 1 over x squared plus a squared, you can use this inverse tan rule, and it's helps you out a lot.